So now I'm starting with another interesting idea of linearizing loads. You can use S or Z, depends on the region you stay in the country, or depends on the region you are in the world. Linearizing loads, and this is covered in SEAP analysis. And what SEAP is? It is from ASHRAE. So for your information, ASHRAE. This is American Society of Heating, Refrigeration and Air Conditioning Engineers. And SEAP means it is a simplified energy analysis procedure. I hope you have got the understanding. It is simplified energy analysis procedure. So what we have is we have simplified the process from the actual process on softwares. It's an energy analysis what we are doing, energy modeling which we are doing, and it's one of the procedure which we can use. So let's start with the idea of linearizing loads. So what we have is, in the earlier videos we have seen the major loads as electrical, solar, occupants, and solar transmission maybe, and the transmission load. We know that the transmission load formula is Q is equal to UA, depends on the beam and all structure. We may have number of hours multiplied or not, but the structure of the formula remains UA into delta T. So that means it is a factor which depends on temperature, while the solar is Q solar is CLTD into UA, cooling load temperature. Oh, sorry. I am very sorry. It's not the CLTD for the solar. It is SHGF, solar heat gain factor into UA. Sorry, into delta. Solar heat gain factor into area. That's all I have. Sorry. Then for the electrical, it is not dependent on temperature. This is also not directly dependent on temperature, but solar heat gain factors are indirectly dependent on temperature, because during the day, starting of the day, maybe at 8 a.m. the solar heat gain factor value will be very low, while at 12 p.m. it would be higher, at 2 p.m. it would be much higher, and then it may start gradually decreasing. Again, depending on the region or depending on the location, at an equator the highest solar rays are received, and hence the location of equator will have SHGF values higher than a location which is 32° north or in the southern hemisphere. So it is indirectly dependent on temperature, but not directly. For the electrical, we do not have any relation with the temperature. It is directly dependent on the amount of lights used. For occupants also, we have nothing directly dependent on temperature. It is directly the amount of number of people and the activity people are doing. And the solar transmission is still dependent on temperature, so it is solar transmission, and it is CLTD, cooling load temperature difference, into UA value. So it is still indirectly dependent on temperature difference. But if we want to do an analysis analysis on a building, what we want to do is we want to have a direct dependence on temperature somehow, so we can easily do all the analysis and estimate the temperature. So if we have a chart like that where there are different temperatures, and this is the load, so these are the different loads which we have. So there are 4 different temperatures which we want to consider. These are TPH, TPC, TIH, and TIC. TPH is the peak heating temperature. This is peak cooling temperature. this is intermediate heating temperature and the intermediate cooling temperature. What I mean is these are the 4 different temperatures. We want to do the analysis or calculation for these all loads and then translate all the values of those loads onto a chart and then linearize it. That is, we have 4 temperatures. Maybe obviously the peak heating temperature is the temperature when the outside temperature is very low. So the TPH starts over here. This is the location for my TPH. That is a very low outside temperature. This is outside temperature graph with respect to loads. So the outside temperature is minimum. At that time we'll have peak heating requirement, peak cooling requirement when my outside temperature is the highest, and the intermediate could be anywhere. It depends. It's our choice. Okay. Now what we do is, this is zero load. These are positive loads. That is heat gain, and this is heat loss from the building because the interest is in the building. That's why. BLDG is the building short form which I am using. So what we'll do is, at the peak heating requirement, we are losing heat from the building, and hence for the solar load we may have a negative solar load. That is, we are losing a lot of heat from the building. At an intermediate condition, let's make a reference line for us. And at an intermediate heating condition, we may have another temperature heat loss from the building. At intermediate cooling, we may have some cooling heat gain from the building because of solar transmission loads. That's what I am considered UA delta T. And the peak cooling may require a lot of heat lost from the building. Let's make a reference line over there also, so it's helpful to us. Okay. So I can make an estimated linearized load. Sorry, I'm extremely sorry for that. And I'll explain you why the slopes are different, because in the in the transmission load we also consider the infiltration itself, which was UA in INF. And the transmission load, which considers infiltration, also has the sensible plus the latent part. So for the latent part, which is dependent on the humidity ratio or relative humidity, it changes non-linearly with the outside temperature. Hence, at a higher outside temperature, the humidity load, the latent load, is increasing much more non-linearly. That's why these slopes are increasing. So this is a higher increase. This increase is lower in the temperature, but this increase is higher in the temperature. At the higher outside temperature, the humidity loads or the latent loads are very high. So this is the transmission load which we have. Now, my internal loads could be again drawn like this. Sorry, that's not the internal load. Internal loads are always constant because these are the electrical loads and occupant loads, and it are always dependent on the average values of the electrical appliances used or the occupants inside. So maybe the electrical loads are constant with respect to my outside temperature, and that's the internal occupant plus electrical. And the solar load is always positive, that is heat gain from the solar load, and with respect to different outside temperature and inside temperature, we may have a solar load which is something like this. And when I add up, so this all things I have considered indirectly on this chart. So when we add up all these loads, what we have is this. we may start with a this is total. So that's the overall total load on the building, considering all the loads which are possible. So this is how we can make an analysis or estimate of all the loads on the building. We have considered all the internal loads and electrical loads, solar load, transmission, and linearize it with respect to temperature. So when we want to linearize a solar load, what's the procedure we follow is, we can take any two opposite or 6 months apart, or actually the months which are representing the peak heating and peak cooling. So for USA, what would be the case would be, we may have a peak heating requirement in January, a peak cooling requirement in July, which are 6 months apart now. We can calculate the value of my Q solar using all the factors, SHGF and area, Q solar value for Jan. Similarly, I'll calculate the value of Q solar for July. So we have two values of Q. And we have the two corresponding temperatures, the TPH and PC. What we want to just do is, we can take Q, we have 2 points, so it is just y is equal to mx plus c, where m could be Q July minus Q Jan upon T July minus T Jan, and C could be anything. Actually it should be the intercept, but we can easily find the C value by again substituting one of the location. So this is how we can linearize all the loads which we have. So similarly, if we want the internal occupants and electrical load to be linearized with respect to temperature, we can still do that using this very simple formula and very simple concept of finding the Q values at the two extremes and then making a linear line between them, because we have the temperatures, we have the loads, so we have the Y and X values. We can just find the M and C values for each of the loads and then add all the linear equations. So if we have all different linear equations like this, which may have my Q transmission as some 2 into T plus 3, my Q solar which will be 3T plus 1, or Q internal equal to 4T plus 1. Taking this all into account, my Q total could be 4, 3, 7, 8, 9 T plus, and T is T outside, that's our X value, 3, 4 and 5. So that's my Q total value. So we can easily linearize all the values, all the loads, and get a total load of my building in a very simple estimate. So that's how we have. I hope you can appreciate the concept of SEAP analysis, which will be very helpful if we do all the analytical solution for energy modeling of a building. Thank you. If you have any queries, do let me know. Thank you.